In this video, we will explore various definitions we use to describe the maximum and minimum values of a function, that is, the highest and lowest values a function can attain.
Consider a portion of the graph of y equals f of x. We might say that the highest value that the function can attain is f of c sub 2. Observe that at point c sub 2, f of c sub 2, the function changes from increasing to decreasing. In such case, the point is called a maximum point. On the other hand, we might say that the lowest value that the function can attain is f of c sub 1. Notice that at point c sub 1, f of c sub 1, the function changes from decreasing to increasing, and in such case, the point is called a minimum point. We can now formally define the maximum and the minimum points as follows. By definition 6.4.1, the point on the graph where the function changes from increasing to decreasing is called a maximum point. Similarly, if we have the following definition for minimum point, note that we simply swap out the increasing to decreasing to increasing, and the maximum to minimum. So by definition 6.4.2, the point on the graph where the function changes from decreasing to increasing is called a minimum point. And by definition 6.4.7, collectively, the maximum and minimum values of a function are called extrema, which means that when we use the word extrema, we are referring to either the maximum or the minimum values. Hence, from the definitions, we can say that the maximum point of y equals f of x is c sub 2 f of c sub 2, which also means that the maximum value of y equals f of x is f of c sub 2. We can also say that the critical number c sub 2 maximizes the value of y equals f of x. In other words, c sub 2 is the number that you would plug into the function to get the maximum value. Or put another way, the maximum value of y equals f of x occurs at c sub 2. With this, you should familiarize yourselves with the distinction between finding the critical number that maximizes the function in which we actually refer to as the maximum value. Similarly, we can apply the same thing with the minimum value. So we can say that the minimum point of y equals f of x is c sub 1 f of c sub 1, which also means that the minimum value of y equals f of x is f of c sub 1. We can also say that the critical number c sub 1 minimizes the value of y equals f of x. In other words, c sub 1 is the number that you would plug into the function to get the minimum value. Or, put another way, the minimum value of y equals f of x occurs at c sub 1. From here, let us set up a more general notion of extrema. Consider the complete graph of y equals f of x with critical number c. And then, let us focus our attention on the numbers nearby c. If we are to magnify that portion of the graph, it clearly shows that c really appears as the maximum value. Now, let us construct an open interval around c. Notice that for all values of x inside the open interval we just considered, it is true that f of c is greater than or equal to f of x, or f of x is less than or equal to f of c.
Now, in this case, we can say that f of c is the maximum value relative to the nearby values, or f of c is the maximum value in comparison only with the nearby values on the graph. In here, f of c is called the relative or local maximum value.
Now, going back to the big picture of the graph of y equals f of x with a relative maximum value f of c. Notice that there is another maximum value f of a in which f of c is less than f of a. In other words, a relative maximum value of a function need not be the maximum value of the function on its domain. Instead, the idea is you can construct an open interval around C, and on that interval, f of C is the highest possible value of the function. And that is what we mean by a relative maximum value. And this inspires the following definitions. By definition 6.4.3, if for all x in some open interval around x equals c of y equals f of x is less than or equal to f of c, then f of c is a relative or local maximum value of y equals f of x. Similarly, if we are after the relative minimum, we only need to consider a very obvious modification. That is, we will swap out maximum to minimum, and instead of f of x is less than or equal to f of c, we will swap it out to f of x is greater than or equal to f of c. Hence, definition 6.4.5 states that if for all x in some open interval around x equals c of y equals f of x is greater than or equal to f of c, then f of c is a relative or local minimum value of y equals f of x. And collectively, relative or local maximum and relative or local minimum is called relative or local extrema. So, if we go back to our graph, you would notice that there are actually two relative maxima, namely f of c sub 2 and f of c sub 4. Hence, we can find two spots on the graph wherein we can construct open intervals on which the function value at that critical number c sub 2 and c sub 4 is the highest value in comparison to the nearby values on that open interval. Thus, in this case, y equals f of x has a relative or local maximum value at c sub 2 and c sub 4. Similarly, it is pretty clear that there are three relative or local minima, namely f of c sub 1, f of c sub 3, and f of c sub 5. Thus, we can find three spots on the graph wherein we can construct open intervals on which the function value at that critical number is the lowest value in comparison to the nearby values on that open interval. Thus, in this case, y equals f of x has a relative or local minimum value at c sub 1, c sub 3, and c sub 5. Now, what about the endpoint? Does it count as a relative maximum? Or shall we ask, is there a relative maximum at this endpoint? To answer this question, let us go back to our definition and see what our definition says about it. In our definition, it says that there have to be an open interval for which the relative maximum value occurs. In other words, we must be able to construct an open interval I that is going to be a subset of the domain of that function. Let us try to illustrate it. Say, we let C be the endpoint in which perhaps the maximum value might occur. Then, let us magnify this endpoint together with the domain D of the function. Observe that if we are to construct an open interval around C and check the condition in our definition, that is, C is an element of I which is a subset of D, notice that it is obvious that on the open interval we just constructed, not all values is inside the domain D. Or we can say that I is not a subset of D. This means that this part of the open interval is not included in the domain of the function, and even shrinking it does not help. Hence, there is no way to construct an open interval at this endpoint. Thus, any open interval that contains the endpoint will not fit inside the domain of f of x. Therefore, there is no relative maximum at this endpoint. Hence, the answer to the question is none. Thus, we should not count endpoints as relative maximum nor minimum. Now, for the final pair of maximum and minimum values, let us again consider the graph of y equals f of x. Again, as mentioned earlier, y equals f of x has two relative maxima, namely f of c sub 2 and f of c sub 4. Notice that between these two values, f of c sub 2 is actually the highest value throughout the domain, which means that no matter where we look at the domain, c sub 2 is going to give us the highest value, which is f of c sub 2. Or another way to say that is y equals f of x has an absolute or global maximum at c sub 2. This leads us to the following definitions. By definition 6.4.4, if for all x in the domain of y equals f of x is less than or equal to f of c, then f of c is an absolute or global maximum value of y equals f of x. Note that c can be anywhere in the domain D including an endpoint. Hence, if we are asked to find the absolute maximum of a function, the endpoint definitely counts. Similarly, if we have the following definition for absolute or global minimum, we simply swap out the maximum to minimum and f of x is less than or equal to f of c to f of x is greater than or equal to f of c. Hence, definition 6.4.6 states that if for all x in the domain of y equals f of x is greater than or equal to f of c, then f of c is an absolute or global minimum value of y equals f of x. And collectively, absolute or global maximum and absolute or global minimum is called an absolute or global extrema. You will learn more about the maximum and minimum values of a function on our next videos. So that's it for this video. See you on our next video.